Welcome back. We are getting to some nice kind of meaty problems, some problems that I think are very wonderful, and we're kind of getting closer and closer to some more real world kind of scenario situations. So let us begin. This is compound interest. You invest $600 into a bank account that has a quarterly compound of 8% every year. We want to write an equation that models this, and then how long until the account has $8,000, right? Well, first thing is, if you need a more in-depth video, again, I would recommend going to E1 on my playlist and looking at compound interest. All right, well, let's start off with what is quarterly compound. Well, quarter means 4, right? That means we are going to have our interest basically multiply, since we're increasing, multiply our balance 4 times in a year. All right, so to do this, we're taking our 8% and we're going to divide it by 4, because instead of 8% per year, we're taking the 8% and we're going to break it up evenly in a year, right? Maybe to show you. Okay, here's 12, 9, 6, and 3, 0. Okay, I'm saying that every 3 months, right, because this is 4, instead of 8%, well, 8 divided by 4 is 2%. Instead of 8% being multiplied once per year, it's going to be broken up evenly 4 times in a year at that new percentage, which is 2% here. Then when it gets to 6 months, we're applying the 2% again. Then at 9 months, the 2% one more time. And then at 12 months, the 2% one more time, right? We're basically going to compound this, right? And that means that once I multiply the interest and whatever my new balance is, it goes and does it again here instead of once per year, multiple times throughout the year instead of once. Well, basically that's the trick. Once we get this new percentage, now we begin. Well, 100% of my starting value, because we're increasing, plus 2%, that gives me 102%. I divide this by 100 and I get 1.02. Okay, that's my new constant multiplier. Now let's start off. Y is equal to, well, 600, and we got 1.02 as my new constant multiplier. And usually we have the t on the exponent, right? But we have to be careful because t represents time, in this case years. But how many times are you multiplying your compound every year? Well, 4, so you have to put 4t. And that's my equation. Now we ask ourselves, how long until the account has $800? Well, we put that in for the output. So how long till it has $8,000. So 8,000 is equal to 600 times 1.02 raised to the 14. Well, what do I do to solve this problem? First, we want to get rid of this 600. So let's divide by 600 to both sides. Okay. It looks like we're going to get 8 divided by 8,000 divided by 600. Let me just see what we get as a decimal. And we are going to get, thank you for the suspense, 13.33333. So let's just do 13.333. 8,000 divided by 600. Yeah, that makes sense to me. All right, is equal to 1.02 raised to the 14. All right, well, let's convert this to logarithmic form now, and let's solve this. Well, you know, the 1.02 is my base, right? So log, and I'm going to put the 1.02 down below here. My base is equal to my input, right? I'm leaving that blank, is equal to my output. Well, your inverse is your output's input switch. So this is your output that now is going to become your input. And since this is your output, well, that now becomes my my input. My apologies, is your input that now becomes your output. So that has to go on the outside. And this is 4 multiplied by t. Well, let's use our little change of base formula, the trick I showed you, to solve this. This is log of 13.333 divided by log of 1.02. And let's figure out what that is, right? So let's grab our handy dandy calculator and let's do log of 13.333 divided by log of 1.02. I forgot the 02. 1.02. So yeah, you could probably hear me clicking it hard. This laptop's not very good. And I get 130.8 80. So let's write 130.80. Well, we're almost done to solve for t. How long does it take? Well, now we got to divide both sides by 4. And when we divide both sides by 4, so let's go ahead and divide by 4. We get 32.7. Look at that. That means it's going to take us 32.7 years. 32.7 years until our $600 becomes $8,000 in that bank account. Pretty crazy. All right, let's go ahead and look at one more example problem for compound interest problems, right? Let's say we deposit, my friends, $2,000 into a bank that is compounded, okay, monthly at a let's say 24% rate per year. Okay, so now monthly, right? Instead of 4 times in a year, well, what is monthly? How many months in a year? Well, there's 12. So this tells me that this is 12. Okay, we want to write an equation, and let's say we want to answer this question, right? How long will it take until account has, again, let's use the same thing, $8,000. All right, but this time with a whole new compound and percentage rate. Well, again, what does that mean? That means every month, pretty much, because there's 12 months in a year, every month we're going to multiply by our new percentage rate, but instead of 24, we're going to break up that 24% evenly. So we can do 24% divided by 12, because this is monthly. There's 12 months in a year, and it says compounded monthly. 24 divided by 12, if we go ahead and do that, that is 2%. Very similar to the problem above. All right, but the compounds is different. So this is 2%, because 12 times 2 is obviously 24. And so let's start again. Well, 100 plus 2% is equal to 102. Divide that by 100. That gives me 1.02. This is my new constant multiplier. So I'll get y is equal to 2,000 times 1.02 raised to the, well, again, we usually have a t here, but how many times are we going to multiply this interest per year? Well, 12 times in that year. So if t is going to represent year, let's put our 12 right here on the exponent. 12 times t. How long until the account has $8,000? Well, we're going to put that 8,000 in for the output, because we want to figure out the time, how long. So we're going to do 8,000 is equal to 2,000, 1.02 raised to the 12 times t. Like usual, let's divide by 2,000 on both sides. And now I don't need a calculator for this one. 8,000 divided by 2,000, that's just 4. So I get 4 is equal to 1.02 raised to the 12t. Now let's convert this to logarithmic form. We're going to get log base, well, 1.02, that's my base. This is your output, okay? And this is your input. So the output becomes your input, and your input becomes your output. Again, let's use our change of base formula, that little trick, to figure this out. Log base 4 divided by log of 1.02. And what do we get? What are we going to get? Opened up the wrong thing. We're going to get, my friends, log of 4 divided by log of 1.02 is going to give me 70. So we're going to get 70 is equal to 12t. Divide 12 to both sides, and we get t is equal to, well, 70 divided by 12. Let's divide that by 12. And we get 5.8. Wow, look at that. 5.8 years, right? That means if we invest more money, if we put more money into this bank at a compound that's monthly at a 24% rate originally, right? But it's compounded. That's why it went down to 2. It only takes 5.8 years. So you see, obviously the bigger the interest rate, the quicker it's going to grow, but also the more compounds. It's going to cause your thing to grow as well. All right. Hopefully that helped you to understand how to use logarithms to help solve some of these compound interest problems.